So obviously inside your calculator you have two options. You've got log base 10 or log base e, which is your natural log. And so if we want to convert into anything else, we need to figure out how to do that. And so if I'm trying to figure out what log base 7 of 60 is, I know that that's some unknown value. From here, we're able to take it from a logarithmic form and convert it into that exponential form. And so this becomes 7 to the x equals our log 60, or sorry, equals 60. So we're going from logarithmic into that exponential form. That's that conversion step we've got a lot of. Now to get the exponent by itself, we can convert it back into an exponential form, or logarithmic form, sorry. And so this becomes the log of 7 to the x equals log 60. So basically what we're doing is just taking the log of both sides. And then Chase, what did we learn yesterday that I can do to get the exponent by itself here? What's that special property we've got that can help me move that exponent? Well, right now I have an exponent here inside of a log. What did we learn yesterday that I can do with that? Good. Okay. So we're able to take that and move it out in front. And so this is the equivalent of x times log base 7, or log 7, not base 7, log 7, equals log 60. And so what's our last step then to get x by itself? We'll just divide by that log 7. That's just a number. So x now is going to equal log 60 over log 7. Okay, so what we've done is we've converted this now into base 10. Okay? And so in the book, what it's going to show you is here's your rule. Here's that equation, the base change kind of rule. You can memorize that if you want to. It's always going to be the same. You've got log of whatever divided by log of your base. That'll get you the base change. Okay. But I don't like memorizing a bunch of stuff, so if you just use those properties you already know, you can rederive this formula every single time. Now, you can also do it with log base e. You're going to get the exact same result. So if we had something like this, right now this is 8 to the x equals 92. That's a 92. And then we take the natural log of both sides. So this becomes x natural log of 8 equals natural log of 92. And then we divide by natural log of 8. So either way, you're going to get to a base change to something you can actually type into your calculator. Now the interesting thing to point out is that is equivalent to if you had done it with logs. And you can type that in the calculator and double check it. But when you are doing the same bases, top and bottom, those are equivalent to each other. It doesn't matter if you do it with base 10 or if you do it with base E, whatever your favorite button to push on the calculator, switch it into that. Okay. So those are equivalent to each other. So anytime you get something weird like this now, you can actually do the base change thing and do it in your calculator. That's the first thing we're going to look at. Just kind of uses a few of those properties to help us identify those. Now, the next piece we're going to take a look at is going to be trying to identify patterns in all that stuff we just looked at with the base change. Okay. So with the base changes, we'll do it 3 times. So first of all, what is this asking? This is asking you to plug 5 in for x, plug 10 in for x, plug 20 in for x. So we're going to take a look at log base 2 of 5. What is that? We're going to look at log base 2 of 10. What is that? And then it's going to look at log base 2 of 20. Okay. And so we know, based on the base change rule we just did, that this is going to be log 5 over log 2. This is going to be log 10 over log 2. And this one will be our log 20 over log 2. And then what it wants us to do is see if we can identify any patterns. So if you type this into the calculator, you'll get a decimal approximation. Ends up being 2.3219. We can do the same thing with the rest of these. This decimal approximation ends up being 3.3219. And this one ends up being 4.3219. Anybody notice any pattern there? Yeah, the first place is just going up by 1. Okay. What did we notice about the numbers? They're doubling. What's the base of my log? 2. So as I double, I go up by 1 exponential growth, so to speak. So similar to like those earthquakes we were talking about, right? We're like, hey, how much larger is a 6.5 earthquake than a 5.5 earthquake? And we're like, oh, it's 10 times larger. Well, that's because Richter scales are based on a log base 10. So as you go up 1 unit, you're actually multiplying the intensity by 10. So since this is a base 2 idea, when we double, we're just going up by 1 in its value. Okay? You'll notice something similar with number 67, the one you guys have to do for your homework. It's a base 3, and we're tripling every single time. So we can start to predict that we're going to see a similar pattern. It's going to go up by 1 every single time. Okay? So that's just one of those things to think about, the multiplication inside of our logarithms and how that connects with what we're doing on the logarithms and their bases. Okay. Next piece is we're going to start getting into some of the uglier looking solving situations. So we're going to start up chapter 5.5 with this. 5.5 is all about solving and making these, being able to actually find the variables. So there's 2 ways you can go about doing this. And I'll show you both just in case one makes more sense to you than the other. But what do you think we can do with this to help us solve for x? We can simplify it, and with that simplifying, what did we do yesterday? It took 2 logs and put them into 1. With the addition here, that tells us that we can multiply this into 1. So we can look at this as log of 4 times our x minus 7 equals our 2. Okay, so this ends up being 4x minus 28 when we distribute that through. Okay, this is in logarithmic form, so we can switch it into our exponential form. What's my base? Base of log, if it's not written, is always 10. So this is going to equal 10 to the 2, or 10 squared. So now we just have 4x minus 28 equals 100, basically, right? And so we're back to a regular algebraic equation. So now we have our 4x equals 100 plus the 28 we'll add over. Okay, so we end up with 128. And then we can divide by 4, so we'll see that x equals 32. I don't even need a calculator for that. That's kind of nice. There is another way, just in case you want to go that route. I'll show you. You could also identify that that's just a number. Okay? I can just move that over and get my variable by itself. So we could write this as log x minus 7 equals 2 minus our log 4. Now we're in logarithmic form. We can switch it to the exponential. This is going to turn into x minus 7 equals 10 to the 2 minus log 4. Okay, so it's kind of an ugly looking exponent, right? But we can do that. And then we just add the 7 up. So this will equal 10 to the 2 minus log 4. And then outside we'll add 7 to it. Now, much uglier looking exact answer, right? But if you type this into the calculator, you end up seeing that it equals 32. So both routes will get you to the same destination. I'm going to recommend you go with this purple route because I think that will lead to less errors and it allows you to do some more cool, complicated stuff with things later when you get variables in both logs. But just know that both these are potential routes to get there. You guys want to see number 8? Are we okay there? All right, couple blank looks. We'll look at one more example. Okay, so if we're doing something like number 8, again, I'm going to recommend we do that purple route. So we're going to do the multiplication step. So we can combine this into one log because it's addition. So this will turn into log of 5 times our x minus 9 equals 1. I'll show all the steps on this. So this simplified out is going to become log of 5x minus 45 equals 1. Okay. We're in exponential form. My base is 10. So this is 5x minus 45 equals 10 to the first, which is just 10. Now you're into your basic algebra. So we can add 45 to both sides. And then we can divide by 5. In this case, x is going to be equally left. So the last piece we'll take a look at today is going to be similar to that, still just looking at algebraic stuff, but you guys remember the uniqueness property we talked about the other week where we said something like, if I have, I had something like 2 to the x plus 3 equals 2 to the 3x minus 5. Okay, we were able to say, okay, they have the same base, so if they're equal to each other, the exponents have to be equal to each other. So that uniqueness property told us we could say that x plus 3 equals this 3x minus 5. And then from there we were able to simplify, get our stuff on the same side. So 2x would equal 8 here, and so x would equal 4. And so we're able to use that uniqueness property to help us solve for these variables in the exponents. Well, the same thing is going to happen with logarithms. If you have the log with the same base of something else with a log, you're going to be able to say that the stuff inside has to be equal to each other. Okay? So more generically, you had something like log A equals log B. The uniqueness property is telling us that A has to equal B. Okay, so in this particular example of 15, we would be able to say that 5x plus 2 equals 2. So in this case, subtract 2, 5x would equal 0. Divide by 5, so x is going to equal 0. We're looking at something like 16, same idea, log base 10, uniqueness property tells us that 2x minus 3 is going to equal 3. We can add 3 to both sides, so 2x will equal 6, and then divide, so x will equal 3. Okay. So, a couple examples on that uniqueness property. And that's what we got.